Hi everyone, my name is David Klee, founder of Sequilibrium. Welcome to Module 9 of my course, the SQL Server on VMware Accelerator. We just wrapped up a good overview of how to tune the Windows operating system, but that's not the only OS that SQL Server can now run on. Let's talk about how to set up Linux properly for SQL Server workloads. In this module, we're going to talk about the specifics around how to improve the performance and operational management if and when you decide to deploy SQL Server on the Linux operating system. We're going to talk about a lot of the similarities with managing SQL Server on Linux that you have running with running SQL Server on Windows, including making sure that the VMware tools packages are up to date, certainly the power profile correctly, handling time synchronization, and storage controller distribution. We're also going to talk about some of the differences, such as setting up the logical volume manager so you can expand the disks as needed in the future, the XFS file system, ways to properly distribute your database objects on these virtual disks, and how to back up your databases to a network share. SQL Server was first introduced for the Linux platform starting with the 2017 release. I for one am incredibly excited to see this because I actually started life in IT compiling Slackware Linux kernels when I was in elementary school. I actually knew the command line side of things before I learned the GUI side of things. PowerShell brought back a lot of the command line activity that we used to use to streamline tasks, and now SQL Server is on Linux. Who'd have thunk it? Unlike a traditional port, the source code was modified with a platform abstraction layer to accommodate running on multiple operating systems. It's actually the full native source code that's running cross-platform. It is almost completely fully featured with the SQL Server engine running on the Windows platform, with a few minor exceptions. Most notably are things that are operating system dependent, like XP Command Shell, that are not present in SQL Server on Linux. I'm actually okay with that, as most of the time we just need the raw SQL Server engine and the agent job scheduler to do everything that we need. My intention for this module is to not give you a Linux fundamentals course, but to show you the things that you can do quickly and easily to make your life easier when managing SQL Server on Linux. Microsoft does support multiple distributions of Linux. A distribution is a variant of the Linux kernel with their own variants of operational management utilities. Most notably is Red Hat Enterprise Linux. Also fully supported is SUSE Enterprise and Ubuntu Server. You may have also heard that SQL Server will now run in a container. A container is nothing more than the application itself without dragging along the operating system, but the operating system still has to be there somewhere. Docker is fully supported to run SQL Server, and Docker contains the underlying Linux runtime so that we don't have to drag the OS along with the container. We can now run SQL Server in a container on just about anything. Docker is fully supported on Linux, Windows, and on Apple platforms. Yes, that means we can run SQL Server natively on a Mac. That's fantastic, especially for development purposes. With the combination of Microsoft development tooling and a SQL Server in a Docker container, we can now develop for the Microsoft product suite natively on virtually any development platform. When running SQL Server on Linux virtual machines, there are a lot of similarities with setting it up and managing it, similar to how you do this on SQL Server on Windows virtual and physical machines. The first step is to make sure that the operating system type is selected properly inside the VMware layer. Again, this sounds like second nature and should be straightforward and obvious, but you would be amazed at the number of places that I see that disregard this setting. There are subtle differences with how the virtual platform manages the different guest operating system types. We want to make sure that all of these layers align properly. Another similarity that we still need is the VMware tools package. Thankfully, this is a little bit easier to manage than on Windows. VMware does ship an official VMware tools package that you can download from their site. There's also an open source package called OpenVM Tools that you can fetch with virtually any of the in-guest package managers. The image on the screen shows you a Red Hat Enterprise Linux server where we can install OpenVM Tools directly from the Yum package manager. It can also be patched without incurring any operating system downtime thanks to the differences in the Linux kernel and the improvements that can be made with zero downtime patching. Linux usually ships with a CPU power profile set to a more balanced mode. Just like with Windows, we want virtualization to be our green enabler, but not at the expense of performance. Every distribution has its own mechanism to tell the operating system to run in a high-performance manner. The diagram that you see on the screen here shows the Red Hat Enterprise specific command called tuned ADM. We can set the power profile to a number of different settings, and I usually find the latency sensitive type to be the best for SQL Server. More details on these options for Red Hat Enterprise Linux is found on the link on the screen, and a little bit of search engine work will find the equivalent commands if you're running a different distribution. Another similarity is that we still need to manage time synchronization. The same rules apply if your operating system time is different from what your application or other components are expecting. Some distributions of Linux still use the NTPD application, and others use a package called Crony. A quick search engine search for your distribution will get you the details. You need to edit its appropriate comp file to specify your NTP servers, and then make sure that the process is running around the clock. If you find that your virtual machine clock drifts more than you care, use this comp file to increase the frequency at which it resynchronizes. Okay, we're going to SSH into the host, and we're going to double check that Crony is installed. This is again Red Hat Enterprise Linux, and they use the Crony package. So DNF install Crony. We'll make sure that this is already installed, and it is already installed. We are going to use the system scheduler to turn on the CronyD package. We're going to edit the comp file and make sure that our NTP server is specified in here. In this case, we're going to go out to the Red Hat Enterprise Linux server, but feel free to modify these for any of your internal NTP servers, especially whatever your Active Directory environment is pulling from. Now, systemctl restart CronyD, and that'll let our system changes take effect. All the discussions that we had around the SQL Server virtual machine directly apply with the storage controllers. My preference for the new Linux virtual machines for SQL Server operations is 4 NVMe controllers if you're on NVMe storage, or 4 paravirtual SCSI controllers if you're on any other type of storage. The driver for these controllers is included with the proprietary or open source VMware tools packages. Most of them are actually including the vScSI controller type into the operating system pre-compiled so that you don't have to worry about injecting the drivers before the operating system is able to be booted up after installation. Just like on Windows, the vScSI disk controller has a default queue depth of 64 and can be overridden up to a value of 254. As with before, make sure that you have a strong understanding of all of the underlying queue depths to make sure that you set this value appropriately. Just blindly setting it to 254 will most likely set you up for trouble and result in increased in-gas storage latency instead of improved. The settings are distribution specific, and you can find more information from VMware directly at the link on the screen. Now it's time to start installing SQL Server. Microsoft has some outstanding instructions on their website for the specific ways to install SQL Server on Linux for your specific distro. The link on the screen will take you to the list that you can select from to provide the specific instructions for your distro. You have to install it and then configure it separately, instead of the traditional way of configuring some base information as part of the installation. Let's get this installed on Red Hat Enterprise Linux. Now we're going to go directly from Microsoft.com and quite literally copy and paste their installation instructions. Again, this is for Red Hat Enterprise Linux. So we're going to add Microsoft's Yum repository to our list. And now, because we have their repository in our list, we can literally yum install Microsoft SQL Server. It takes about 30 seconds to a minute and a half, depending on the speed of your systems. I sped this up to keep this video fairly short. Now, we need to configure this with things like our SA password and making sure you agree to the license agreement. So MS-SQL-Conf setup, pick your edition here. Do you accept the license terms to make everybody's lawyers happy? Enter your SA password. And we are now up. We're going to double check the status of the MS-SQL Server service. And it is up and listening. We're going to add a hole in the firewall, and then we're going to reload the definition so that it allows 1433 through. Now we're going to add an additional repository in here. And we're going to do this so that we can install some MS-SQL tools, an ODBC driver, and then eventually the SQL agent. And again, you have to agree to their license. We're going to add the path, similar to what we do in Windows, to make sure that we can use these tools pretty much from anywhere on the system. That installed our SQL Server. And now we're going to configure the SQL agent. So literally MS-SQL-Conf set SQL.agent enabled equals true. Restart SQL Server with the command there. And now we can double check our instance, and you can connect with SSMS, or Azure Data Studio, or any other tool you like. And if you take a look, not only did that pull the correct SQL Server, but it also pulled the SQL Server with the latest cumulative update slipstreamed in it. Our SQL Server is up. And you can see from the instance properties, operating system Red Hat Enterprise Linux. It's pretty amazing. And as you go through the instance level defaults, you can see there's really very little different except for our default paths in there. But we'll go take care of those momentarily. Here's where things start to get a little more interesting. These drives that we added for our SQL Server objects don't just start working on their own, just like in Windows. It takes a little bit of work with some of the more nerdy components of Linux to get these disks ready to go. The concept of distributing your SQL Server objects amongst multiple virtual disks is certainly not new. We have multiple disks and multiple controllers and hope that you've gathered enough information to understand how the objects need to be distributed on this new platform. Every new disk that we add is assigned a block-level physical disk assignment. You can see this virtual machine has 4 virtual disks because we have 4 objects named SDA, SDB, SDC, and SDD. Instead of numbers, these are assigned letters with the storage device A, B, C, and D. You can see that a storage device has a number of partitions on it labeled SDA1, 2, and 3 with the file system type listed next to it. This is where a root operating system is installed. Note that I say root because Linux is a lot more logical in its disk layout than a traditional Windows machine. I mean, who in their right mind would have installed an operating system disk on a disk starting with the letter C instead of A? Linux is much more logical in that the root partition is literally a slash, which you can see as the REHL root XFS file system partition underneath SDA3. The other boot partitions are located under /boot, /boot EFI, and home. There's also the equivalent of a Windows swap file listed as just swap. All of our new disks that we will need to add will have partitions created under each of these disks, and we'll mount them to mount points where appropriate for our SQL Server objects. The standard SQL Server object distribution rules still apply here. Multiple virtual disks for our individual SQL Server object needs and balancing them amongst the multiple available controllers is critical to helping long-term stability and performance. Whereas on Windows, we can use perfmon to help us understand our resource consumption rates, on Linux we can use the commands syststat and iostat to help us understand our resource consumption patterns to help us better balance our objects. As with before, standardize your deployments to make sure you know exactly where things are out and document any deviation. If we were just to create a regular partition, we would not be able to expand them in the future by default. We need that ability to grow this virtual disk as needed as we know our volumes of data continuously grow. We also don't want to just overallocate like we did in the past. What we need to do is to use a construct called the Logical Volume Manager, or LVM, to create a volume group and then an expandable volume per virtual disk. This allows us to have functionally the same level of operations as a SQL Server on Windows virtual machine. Before I show you how to set all this up, we need to talk about the supported file systems. On Windows, we have the supported file systems for NTFS and REFS. On Linux, we have 2 as well, ext4 and XFS. I prefer to use the XFS file system type as it has a larger block size and seems to perform a little bit better for our large individual SQL Server object files. Now let's take a good look at how to set these up and format them properly. Now, this next task is not the easiest. We have to make sure that we can set up our disks in a way where they can be expanded and moved around after the fact. By default, we don't get that with Linux, so we are going to sudo su as root so that way every command is running essentially with administrative permissions here. We're going to list all of our block devices, and you can see we have our 4 disks connected to the SQL Server. We're going to do a Logical Volume Manager disk scan so we can see the individual disks. We're going to create 3 different disk pools. Now, we're going to create a Logical Volume Manager volume group called tempdb on disk B. We're going to do the same thing for data, and then we're going to do the same thing for logs. Now we're going to create a logical volume on here with the logical volume manager. We're going to use all free space on each of these logical volume manager groups. Let's list our block devices again, and you'll notice now for each of the disks, we have a logical volume member under each one. If you list /dev, which is devices, you can actually see these items under there in blue on the right. Now, we're going to format these with makefile system XFS, and we're going to format each one of those with the XFS file system. We'll do data, then log, then tempdb. Now we're going to go into the SQL Server root folder, and we're going to make folders here that correspond to each of those volume groups. So data01, log01, tempdb01. We're going to change our owner with a recursive parameter to msql.msql. That's our user and our group, and we're going to do that for each of these three folders. Linux is really strongly secured, so this makes sure that our service account, the SQL Server service, can actually access these folders. Now we're going to edit our file system table, or etcfs tab. We're going to add 3 entries under here for each one, and you can see this simply maps the folder and mounts those logical volumes as XFS defaults. We're going to mount each one of these because we have the entries in the FS tab table. At this point, instead of, E, F, G, we now have mount points under the SQL Server mounted folder corresponding to data, log, and tempdb. Not too shabby. That's how we use these extra disks in Linux. Now, what happens if we need to expand these? This is the magic. We have our 3 data, log, and tempdb disks. We're going to double the size from 100 to 200, and then 160, and then 120 gigs respectively. With Windows, it's easy, right? Click expand, you're done. With Linux, not quite so easy, but it is straightforward. We're going to log back in, and we're going to go back to our super user. Look at disk free for each one of these things. We're going to go back, and we're going to list our block devices again. So you can see there, 100 gigs, 80 gigs, 60 gigs. It doesn't know how to do a scan to find the free space, but this command here will take care of that for you. And we're going to scan each one of these drives specifically. Now we're going to PV display, and we're going to look to see here, can we see our free space? And you'll notice right now it has scanned and has seen it, but now we need to expand our volumes to fill this space. So now PV resize, and then simply resize each disk. Boom, it's scanned and it's now resized. And if you take a good look, it now is fully aware of the extra space that we just added. No downtime, no impact, no problem. Now we're going to extend the logical volume to fill the physical disk space extension. So for our data, we're going to add that 100 gigs that we added. And then we're going to do the same thing for our logs and then tempdb. And that was 80 gigs and then 60 gigs. And now let's list our block devices again, and we're going to see our free space. Not too shabby. That is how you can expand disks in Linux and have exactly the same functionality that you do in Windows. Not the easiest to set up, but it is straightforward, especially if you follow the directions here. Now that we've got our virtual disk set up properly so that we can expand these in the future, and we know that our SQL Server objects need to be distributed, let's learn how to do this on the Linux platform. We don't have a GUI folder option inside the SQL Server Management Studio. We need to use that configuration tool msqlconf to set a lot of these parameters, including the default data and log directories. Let's take a quick look to make sure that we know how to set this properly up by default. We need to change the default locations for database data files and log files are automatically created if a location is not specified. Normally, we could do this by going into the instance level properties, go to database settings, and then specify our data and log default locations. But on Linux, we can't do that. We have to go to the command line, SSH into this server. Now we are logged in as root. Let's go to opt msql and then run msqlconf set file location.default datadir, and then specify that new disk and that mount point that we just added. Go ahead and do the same thing for our logs. Once you've applied these, you can literally copy and paste the command right there to restart SQL Server. And that's it. Nice and easy. So you'll notice now here in the instance level database settings, our locations have changed. Now let's create a dummy database here so I can show you that this actually works. So just simple. Right click, create new database. We're just going to call this testdb01. You notice we do not specify anything, but if you look there, our paths are set properly. And now if we go back to the file system, we're going to take a look at our mount points here. We'll go to our data, and there's the MDF file exactly where we wanted it to be. The same thing goes with moving our tempdb data and log files. We need to move the SQL Server data and log files to one or more of our tempdb virtual disks. Let's take a quick look at the differences between Linux and Windows in this operation. One last thing to worry about is that we need to go ahead and relocate our tempdb database data and log files. Now you'll notice here's the command. It looks exactly to the regular syntax, except for our file names show our paths as var opt msql data tempdb01, one of those new mount points that we just created. So if you run this, it works just like in Windows. Go ahead and restart SQL Server to let this take effect. And then just like in Windows, it's moved it, but it hasn't cleaned up after itself. So if you look at the tempdb database properties, you'll see under files here that it has successfully moved everything. var opt msql data tempdb, that is our new physical virtual disk. There's our files on the file system. Now if you go back one, you'll notice it didn't clean up after itself. So we're just going to go ahead and remove all these. We can put a question mark in there and do each file individually since they're sequentially numbered. And now tempdb.mdf and templog.ldf, and we have now cleaned up and successfully relocated our tempdb. One last change is related to how we back up a SQL Server onto a network share to get those backups off of this machine in the event of an emergency. Windows can communicate with an SMB share natively, but Linux can do this with setting up an interoperability utility called Samba. We can define credentials in a safe location that'll match our Windows security on the share, and then set up an FS tab entry for a local mount point. SQL Server thinks it's writing backups locally, but it's passed through directly to the network share. Let's learn how we can set this up. My preferred backup to disk target for our databases is a different machine somewhere on the network. We're going to install Samba on here. So in this case, Red Hat Enterprise Linux, we're going to yum install the Samba client and Samba common libraries. It's already installed here, so it didn't have anything to do. We're going to go ahead and cd into the SQL Server folder. We're going to make a mount point for this network share, just in this case, backup 01. We're going to manually mount this to make sure that we can see it. So mount with the CIFS protocol. We're going to specify a username, and this is going to be / server name or IP / share that we want to connect to. And then we're going to specify the local mount point. It asks you for your credentials, no big deal. This is temporary just to make sure that we can see it. So if we look at disk free, it's actually scanned. It sees there's 30 terabytes available on this share, and life is good. We're going to change the owner of this mount point so that way our SQL Server service can get to it. But now we need to make this mount persistent. And we can do that very carefully. We're going to create a credentials file in a location that is highly secure. Nobody can get to it. This is under the root folder. We're just going to call it SMB credentials. You can call it whatever you want. And it's literally an NTLM username and password. We're also going to make sure that that is not readable by anybody but the root user. Now we'll add an entry in the etcfs tab. And if you notice down at the end there, / server machine or folder, the local mount point, CIFS, and then a bunch of different parameters in there, including read-write, non-permanent, credentials, and our path to that credentials folder. And now, because it's in the etcfs tab, we can mount that mount point and now see everything. There we go. So now, to back this up, we literally just back it up to a local folder on this machine, except it's actually over the network. And you can see the backup command runs just like normal. In fact, we can actually browse to the share, and there's our file. Nice and easy, nice and straightforward. See? Running SQL Server on Linux really isn't too challenging. At this point, it's really business as usual for SQL Server operations. Review your SLAs, see if you need to enable any SQL Server high availability features, and make sure your backups are set to backup properly. Performance tuning falls under the SQL Server engine, so you're good to go. The next stop is to set up our SQL Server instance so that it aligns properly with our physical and virtual machine compute resource topology. That's going to be a big one. Stay tuned.